Hello, everyone. I'm delighted to have been invited by the VCL workshop to give this presentation. In this presentation, we introduce our method, Visual Domain Adapter, VIDA, for the continuous time adaptation in the semantic segmentation track of the first Visual Continual Learning Challenge and ICCV 2023 workshop. Here is the whole content for this presentation, which includes the following 5 sections. So first, we will introduce the CTTA problem. A classical source-free DA task, test type adaptation, eases the distribution shift between a source domain and a fixed target domain. This is typically achieved through the utilization of self-training mechanisms. However, when adapting to continually changing target domains, pseudo-labels are noisy and the updated model parameters become uncertain, leading to error accumulation and catastrophic forgetting. To tackle this problem, continued test and adaptation, which is called CTTA, has been proposed, which addresses a sequence of different distribution shifts over time rather than a single shift as in TTA. Furthermore, CTTA also encompasses the efficient continued adaptation of foundation models to continue downstream tasks or distributions. Existing CTTA works have primarily employed model-based or prompt-based approaches to extract target domain-specific and domain-shared knowledge simultaneously. However, for model-based methods, the noisy pseudo-labels are still unreliable and play a limited role in avoiding error accumulation, particularly in scenarios with significant distribution gaps. Meanwhile, prompt-based methods face difficulties in leveraging soft prompts with limited trainable parameters to learn long-term domain-shared knowledge and prevent catastrophic forgetting. Here is the whole framework. Drawing from the insight that mean teacher predictions are often more robust than standard models, we utilize a teacher-student model framework to ensure scalability during continued domain adaptation, which also presents a fair comparison with previous CTTA works. The overall framework and the details of our method are shown in the figure. We inject a variety of visual domain adaptation models, which is called VIDA, each representing distinct domains, into the linear layers of a pre-trained source model. VIDA updates are achieved through a teacher-student framework using a pixel-level consistency loss as the optimization target. Specifically, the student model operates on the original image, while the teacher model works with an augmented version of the same image. Additionally, the teacher model is updated using the EMA. The details of the visual domain adapter are shown following. The CTTA specific adapter design is following our new paper. VIDA, homostatic visual domain adapter for continued test and adaptation, which achieves 2 weak accept and 2 borderline accept rating in NeurIPS 2023. To tackle these CTTA limitations and maintain the model plasticity, we tactfully design a homostatic visual domain adapter shown in the figure, which explicitly manages domain-specific and domain-shared knowledge in the continued adaptation process. The design principle of injecting VIDAs into the pre-trained model is simple yet effective, which is illustrated in figure. As we can see, there are 3 sub-branches. The linear layer in the middle branch is originated from the original model, while the right branch and the left branch are bottleneck structures and separately indicate the high-rank VIDA and low-rank VIDA. Specifically, the right branch contains an up projection layer and a down projection, while the middle layer dimension of high-rank feature are larger than the original feature dimension. There is not any non-linear layer in the VIDA, and we utilize the linear layer as the projection layer while the original model is transformer architecture and adopt one-by-one trump as the projection layer when the original model is a convolution network. In contrast, the left low-rank branch first injects a down projection layer, then places an up projection layer, while the middle layer dimension of the two-rank feature is equal to 1. Specifically, we first carefully explore the different domain representation of vidas with trainable high or low dimension embedding space in the middle layer. As shown in the feature distribution in the figure, we conduct a TSNE distribution analysis for the different adapter representations across 4 target domains, ACDC. The 4 different color means different continual target domains. The low-rank branch exhibits a consistent distribution across the target domains, suggesting that it can effectively disregard the impact of dynamic distribution shifts. Our observations reveal that vida with a low-rank embedding space focuses on task-relevant feature representation, showing trivial distribution distance in different domains and neglecting the influence of dynamic distribution shifts. Conversely, vida with a high-rank feature concentrates more on extracting domain-specific knowledge, as evidenced by the feature distribution in different target domains showing an obvious discrepancy. We provide a detailed explanation of the motivations in the following slides. Furthermore, we adopt the domain distance definition proposed by Ben David and build upon previous domain transfer research by employing the the H divergency matrix to evaluate the domain representation of adapters across different target domains. Similar to previous work, we adopt the JS divergency between the two adjacent domains as an approximation of H divergency because it has been shown to successfully distinguish domains. If the inter-domain divergency is relatively small, it can be demonstrated that the feature representation is consistent and less influenced by cross-domain shifts. We compare the JS values obtained by using the source model alone, injecting a low-rank adapter, injecting a high-rank adapter, and combining both high-rank and low-rank adapters, as illustrated in the figure. Our results indicate that the feature representation generated by the low-rank adapter exhibits lower divergency compared to both the original source model and the high-rank adapter, especially when dealing with later target domains or significant domain shifts between adjacent domains. This result simultaneously demonstrates the low-rank adapter's ability to learn long-term domain shared knowledge in a continually changing environment. Inspired by intra-class dissimilarity proposed by K-means, we used normalized intra-class divergency to further verify the domain representations of high-rank adapter in cipher 10C. In a given domain, if the intra-class divergency for each category is smaller, it demonstrates that the model has a better understanding of the current distribution. As illustrated in the figure, the high-rank adapter is found to drive down the intra-class divergency with almost all domains, indicating that it can better adapt to current domain distribution and extract domain-specific knowledge in continual target domains. To provide clearer evidence for the intuition, we extend our analysis by incorporating the qualitative analysis of a class activation mapping on the ImageNet to ImageNet CCTTA, as shown in the figure. We showcase the feature representation from different target domains, including the noise of Gaussian and snow. We observe that the low-rank vida is inclined to put more weight on the foreground sample, while tending to disregard background noise shifts. This indicates that the low-rank vida attends to locations with more general and task-relevant information. Conversely, the high-rank vida exhibits an inverse pattern, as illustrated in the figure. It allocates more attention to locations characterized by substantial domain shift, encompassing the entirety of the input images. This behavior aligns with the Harvard branch's tendency to fit global information and extract domain-specific knowledge from the target domain data. In conclusion, the structure of low-rank data reduces feature redundancy, which leads to an underfit state during CTTA. Consequently, it tends to acquire general information across continuous target domains, extracting task-relevant knowledge to mitigate catastrophic forgetting. In contrast, high-rank data employs a higher dimensional feature representation that better aligns with the target domain target data distribution, thereby focusing on learning domain-specific knowledge to prevent error accumulation. This is a simple verification about our proposed low-rank and high-rank readers. For more details of our intuition justification, please refer to our paper. So here is some implementation details of our method. We follow the implementation details of quota to set up our semantic segmentation CTTA experiments. Specifically, we use the SETR as our segmentation model and integrate a pre-trained foundation model, segment anything. Our experiments are conducted on shift dataset. We resize the original image size to 1024 by 1024, which serves as the network input. And we also evaluate on the same resolution. We use a range of image resolution scale factors for the augmentation method in the teacher model. The optimizer is SGD, the learning rate is 0.01, the batch size is 2, and all experiments are conducted on A100 cars. Here are some metrics. We all follow the challenge metric to evaluate our methods. So on the leaderboard, our method achieved an impressive 74.3 overall score with 84.6% MIOU and only a 5% MIOU drop on the shift test set, securing the first place on the online leaderboard. Here are some numbers of our experiments. The table 1 shows the performance of the different methods on the shift datasets continuous validation set CTTA. We evaluate 3 domain shifts: daytime to night, clear to 4D, and clear to rainy. We chose the challenge baseline Deep Lab V3 and our method for online testing on the shift dataset, continuous validation dataset. Table 2 shows the result on test dataset. From the results in Table 1, it can prove our method has better performance on CTTA tasks. The foundation model SETR achieves a similar MIOU to the baseline method, Deep Lab V3, but when we integrate a pre-trained foundation model, segment anything to SETR, the initial generalization ability of our SETR gained a significant improvement. This gives the model a more stable semantic segmentation over a consistently changing domain. In further experiments, during continuous test time, we add low-rank and high-rank readers to our SETR and end up getting a gain of 23.7% on MIOU. This excellent result shows that readers can mitigate error accumulation and catastrophic forgetting. On the results of the online test phase, Deep Lab V3 overall score is only 9.5, and our method overall score is up to 74.6. In this continuous domain shift scenario, the difference between Deep Lab V3 in the segmentation effect of the source frame and the target frame is obvious, and it is apparent that the model does not learn enough domain-specific knowledge, which leads to its high MIOU drop. On the contrary, our method owns the SM pre-trained strong generalization ability, and the addition of vidas allows the model to continuously learn domain-specific and domain-agnostic knowledge. Hence, our model can better adapt domain shift in test time, and its MIO drop is only 5, which also indicates our method maintains the model's plasticity better on CTTA tasks. Here are some visualizations. In order to show the ability of continual adaptation of different models more intuitively, we visualize the test results of all the experiments on the shift continuous validation set as shown in the figure. Our method achieves a better segmentation map. So here are more visualizations. In this report, we propose, so here are some conclusion. In this report, we proposed the method achieves very competitive results on the continuous test time adaptation for semantic segmentation track. We are very grateful to ICCV workshop for organizing this visual continuous learning challenge and hope that our work will inspire more CTTM methods to achieve better performance on the Shift dataset. Thanks, everybody. Finally, for Dr. Liu, we not only lost a rising star in academia, but also a genially kind and cheerful soul. Hearing this distressing and sorrowful news, we grieve her departure and fervently hope she rests in peace.